In this video, we're going to take a look at some application problems involving exponential growth or decay. So our formula that we use is A equals P times 1 plus R for growth and 1 minus R for decay, and then all raised to the power of T. So let's write down what those variables represent for a minute. So A is your final amount. P is your principal amount or your initial amount. R is your rate, and then T is time. Okay, so let's look at some examples. First, you want to read the problem and determine, is it a growth problem or is it a decay problem you're looking at? So for example 1, it says the annual rate of increase for the U.S. population in 2000 was 1.24%. The U.S. population in the year 2000 was 281 million. Use the model to predict the population in 2018. So the key word here is increase. And so we know we're looking at a growth equation, a growth model for this U.S. population problem. All right, and so let's write down the right formula. So A equals P, it's growth. So let's do 1 plus R to the T power to get set up properly. And it says the population in 2000 was 1.24% was our rate of increase. And so for rate, you always want to change it to, instead of a percentage, we want to make it into a decimal. So you can just move the decimal over 2 places to the left. So it'll be 0.0124. You can also take the 1.24 and divide it by 100, and it will do the same thing. But you want to make your rate into a decimal. That is very important. It's just because our calculators don't handle percentages. So we must make the rate into a decimal. So the U.S. population in the year 2000 was 281 million. All right, so that would be our initial population. All right, so let's put the initial population is 281 million. We know it's in millions, so let's not put all those zeros. We're just going to have our answer that will also write in millions. And let's put 1 plus the rate, which was 0.0124, and then time. So notice they said that the year 2000 was when we are looking at this initially, and we want to predict the population in 2018. So from 2000 to 2018, 18 years have gone by. So that's your time. So T would equal 18. And then 281 million, that was your P value, your initial amount. All right, so all we have to do from here is type it in our handy calculator, which we can just continue to use Desmos for this. We're just not graphing anything. So if something shows up on the graph, just ignore it, but I don't think it will. So let's type in 281, just like it looks on my paper, 1 plus 0.0124, and then to the power of 18. And then we have our answer. So we have 350, and let's just say 0.8 million is our population we're predicting for 2018. Okay, next example. It says, suppose you want to buy a used car that cost $11,800. The expected depreciation of the car is 20% per year. Estimate the depreciated value of the car after 6 years. Okay, so the key word there is depreciation. So decay, decrease, depreciation, those all sound really similar to one another, and they are. So we need the rate of depreciation, or our formula is decay. So let's put A equals P, 1 minus R to the T power is our setup. And we'll fill in what we know. So our initial value was 11,800 for our car. Our rate, we got to figure out. So 1 minus, and let's put the rate into a decimal. So if the rate is 20%, and we move our decimal over 2 places. So right now it's sitting behind that 0, and we need to move it to the left. So that would be 0.20 or just 0.2 is also okay. All right, and then time. So to model this function, you would want to leave that little t right there. So if they ever ask what is the model to represent the situation, then that would be it. But we want to go ahead and fill in what would be the value of this car after 6 years. So let's just go ahead and fill in the time is 6 for this case. And let's type it in Desmos. So I'm going to just type in 11,800 parentheses 1 minus 0.2 to the 6th power. And I get $3,093 and let's round to 30 cents because that would make sense with money. All right, so we get the value of the car after 6 years. So that was decay, population was growth. Oh, we're back to population again. That's a really popular type of problem for growth. But let's see, a population of 100 frogs increases. There's a key word there. So it increases at an annual rate of 22%. So if we have increasing, that's growth. Let's write down our formula. A equals P 1 plus R to the T power. And then let's put in things that we know. So our initial amount was the 100 frogs. So we don't know the final amount yet. But we had 100 frogs, 1 plus the rate of 22%. So 22%, if we move that decimal over 2 places, would be 0.22. Always change your rate to a decimal. And then let's put T, because this is the model of the situation. And it's important to know the difference between a model of a situation and then how to get your answer, which they're very related, but not quite the same thing. So let's fill in the 5 years and answer our question now. So let's type in 100 frogs, 1 plus 0.22, close your parentheses, and then to the 5th power. So we would have, now think about frogs here for a second. You can't have part of a frog, so let's just round this off to a nice whole number this time. So we would have 270 frogs. Okay, our last example here says in 2019, a 128 gigabyte iPhone X would have cost $1,488. It is found that it depreciates. So there's your keyword. It's a D word that goes with decay. It depreciates at a rate of 33% per year. Oops. Sorry about that. Let's see. How do I get that to go away? There we go. Okay, sorry about that. I just clicked on something by accident. Okay, back to business. So we had depreciate. So let's write down our formula for decay. So A equals P times 1 minus R to the T power is our formula. Our initial cost of our iPhone was $1,488. Let's calculate what the rate would be as a decimal. So 33%, just move your decimal over 2 places to the left. So that would be 0.33. And then again, let's write the model of our situation first. So just leave T and leave the A. It's like your X and your Y are still there, but we're just writing them with different letters today. So then let's calculate the answer to this question, which would be after 2 years. All right, so we type it in. We got 1,488. 1 minus 0.33 squared. All right, and so we get that this iPhone would depreciate to a low value of $667.96. So it depreciated quite a bit from that original amount. All right, So let's just look at a few more quick examples. And I think I can just move my calculator out of the way for now. Okay, so if we are given this function for number 1, and it says y equals 1200, 1 plus 0.3 to the t power. It says, does this function represent exponential growth or decay? And so looking at the 1 plus the rate right there, I would say that this one is definitely exponential growth. And then they said, what is your initial value? So you can look in your formula and see that the initial value is like the 1200 there. And we don't know if that's money, so I'm just going to put the number. And then what is the rate of growth or rate of decay? So that is this number right here that we added or subtracted. So it's 0.3, and we know it's a rate of growth. And remember, you could write that as a percent. So you just convert it back to a percent by moving your decimal over 2 places to the right. So we could say it's 0.3 or 30% rate of growth. Okay, so let's do 2 more of those for these notes. Does this function represent exponential growth or exponential decay for number 2? So we have y equals 55 times 1 minus 0.02 to the t power. So minus means this one is decay. What is your initial value? So remember, that's usually just sitting right out front of that parentheses. So that would be 55. And then what is the rate of growth or decay? So you pick out this number that's being added or subtracted. So it is a rate of decay, since this is a decay function. And then it's 0.02 is your rate, or you can change that back into a decimal, or excuse me, a percentage. So move your decimal over 2 places to the right, and so it would be 2%. So 0.02 or 2% is our rate of decay. Then let's do one more of these. And number 3, it says y equals 100 times 1.25 to the t power. So this one looks a little different, but let's think about it. 1.25 is bigger than 1. And so if we just separate that, we could rewrite it as 1 plus 0.25, and then it might be easier to take a look at. So that is growth. Since it's bigger than 1, it's adding to the 1 by 0.25. What is my initial amount? So that one's still pretty easy to pick out right out there in the front. So that's just 100. And what's the rate of growth? So now that I've rewritten it, it's probably easier to look at. So rate of growth, since this is a growth function, would be 0.25, or move your decimal back over to a percentage and say 25%. So when you're talking about the rate, you might need a percentage or a decimal. So it's good to be able to go back and forth between those two. All right, so that's it for this set of notes.